Hey there, welcome to Geography, and this video is an introduction to cartography. We're going to look at the theory of cartography, elements of maps, common types of maps, geographic information systems, and also something called remote sensing, which is used to help make maps. So in this picture, you see a famous painting by Johannes Vermeer from the Dutch Golden Age called the Geographer, where you see a guy looking out the window and he's got a map in front of him. He's making maps. This time, the Dutch were going around the world, establishing an empire, and they were very, very good at sailing, and many of the best cartographers at that time were Dutch. Cartography is a study and practice of making and using maps. It comes from the French word carte, which means map, and graph, from the Greek, to draw or to write. So it's literally to draw or write a map, cartography, the study and practice of making maps. And maps are the primary tool of geographers. Just like in history, we have timelines are the primary tool that tell us when things happen. And then historians try to figure out why things happen and why that matters. It's the same thing in geography. You start with a map that tells us where things are, but then the geography part is to figure out, okay, why are they there and what matters about that. One of the key aspects of maps that makes them special is that they're synoptic, syn meaning together, and then optic as in visual, meaning they show many things at the same time. And when you put many things at the same time onto the screen or onto the page or onto the map, then you can make connections among them. Sometimes I ask people, can you imagine if you had to tell somebody this map, meaning the information on that map? Could you just explain that to somebody if they couldn't see it? It'd be very, very difficult. The spatial relationships in there, what's related to what else, is very difficult to explain in just words. You really need to visualize it and see it in front of you. The founding editor of National Geographic, Gilbert Grosvenor, has a famous quote: "A map is the greatest of all epic poems. Its lines and colors show the realization of great dreams." When you look at this map here by a famous cartographer named Ortelius from 1603, a Flemish cartographer, you can see the information that he took in from people who went to Iceland and then came back to mainland Europe and told them what was up there. Some of it's on target, some of it's a little bit maybe off, perhaps, but this is the realization of great dreams. Think about people that had to make that voyage from mainland Europe up to Iceland, explore, chart what they found, bring it back, and then explain it to that cartographer who then could put it down. Cartography is both an art and a science. It's a science because there's a lot of mathematics involved in putting the world onto a two-dimensional surface, but also at the same time, it's also an art because there's many, many choices that have to be made about what to put on the map and how to put it on there. And that first part is very important, just figuring out what to put on the map, because what you leave off is also very important as well. If you try to put everything on a map, it's going to backfire. It's going to be cluttered and look like spaghetti. So you have to be careful about what you want to put on the map to make it the most effective so that the viewer gets the point. Let's look at some of the map elements. These are elements that you typically find on a map, and not always, because there's no map police coming around ensuring that everyone puts the same elements on a map. But at the same time, these are the elements that on a real sophisticated map, you would want all of these things, hopefully, on that map. There's all different levels of maps and different needs depending on the audience. So first of all, you need a title. We'll talk more about titles in a moment. Talk more about all of these in a moment. You need a legend or a key, which explains the symbols. You need the map scale to tell you the relationship between the real world distance and map distance. You need something to tell you the direction, usually, like a north arrow or what you call a compass rose. If it's a map that comes from data that was collected, then you need to have the source of that data and who created the data. You need to put the projection, which is something we'll talk much more about later and also in another video. It's the way, the mathematical method through geometry of getting the three-dimensional globe onto a two-dimensional surface. You need to have the neatline, which is the box around the map that shows the end of the map and where the paper, where it's just paper after that or just screen. And you need to have the graticule, hopefully, which is the latitude and longitude lines. This map does not have a graticule on it. And then you need to have credits, meaning whoever created the map. So let's look a little closer at those map elements. The map legend or key is like a visual dictionary explaining the symbols. It could be 2 symbols, there could be 22 symbols, there could be 300 symbols. There's no international official code of symbols that everyone's supposed to use, but some of them come up a lot. For example, parking lot, a big P and a square. There's a slight difference between a legend and a key. A legend is for things that are generic, very general. For example, a golf course. Any golf course has a golf course symbol, like you see on the map there under activity. But if something is specific, right, if you have just as one symbol for one particular thing. For example, if you have a symbol with a little Eiffel Tower in it, and then on the map it's got the Eiffel Tower, there's only going to be one Eiffel Tower. And so that's a key. So a key has unique symbols and legends have generic symbols. The map scale shows the relationship between the distance on the map versus the distance in the real world. Okay, so the distance on the map, how does that relate to the distance in the real world? So for example, on this map here, what that's telling you, that little line like this, is called the bar scale, is simply telling you that whatever that is, however long that orange line is on the top, that's 60 miles in the real world. So if you got that on the screen right now and I take a ruler and measure it, it's like an inch or something like that, then 1 inch on that map is 60 miles in the real world. There's a relationship there, a ratio. So that's what the map scale is designed to show. There are different ways of expressing that map scale, the same scale, but just different ways of expressing it. For example, you could say 1 centimeter on the map equals 30 kilometers. You can write it out like that. That's called a verbal scale. You could have a ratio, same thing, 1 to 300,000. Or the same way, a representative fraction, 1 over 300,000. And notice that on those, there's no units. So the verbal scale, you have the units, centimeters to kilometers. But if you have a ratio or a fraction, you don't even need the units. It's just whatever. Anything that's 1 on the map is 300,000 times bigger in real life. And then, as we said, there's a graphic or scale bar where at the bottom there, where you just literally just show the bar, and whatever length that bar is, that's whatever it tells you it is in real life. So on the bottom, it says 30 miles is the length of that bar. That's it. It doesn't even matter how long it is. You have to measure it even necessarily. You just know that that length, you can eyeball it, is 30 miles in real life. And what you can do when you have a map scale bar like that is that if you really want to know how far things are apart on the map, you can get out a ruler, measure that map scale using your ruler, and then mark that down on, say, a piece of paper or something like that, a little distance, and then just go bop, 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 take it along, see how many of those you need to get from point A to point B, from New York to Boston, or from DC to North Carolina, whatever it is. And then just look at the map scale, say, okay, that's 30, each of those, and just 30, 30, 30. You can see how far you've traveled. The closer you get to a map, the more you zoom in on a map, right? The more you zoom in and objects get bigger and bigger, you're getting closer and closer to a 1-to-1 map scale. So like theoretically, a 1-to-1 map would be the map is the same size as the actual world. When you say a map is a small scale map, it literally means that the scale number, right, the fraction of the scale that you see there, says representative fraction, is a smaller number than another map. So for example, at the bottom, it says 1 over 1.3 million. And the top number is 1 over 94 million. So 1 over a bigger number, it's 1 over that. It's going to be smaller and smaller and smaller, right? Because the bottom of the fraction keeps getting bigger and bigger and bigger. Hence, the total number there together, 1 over 94 million, is a smaller and smaller number. Hence the name, a small scale map, okay? But another way to just remember that, which is not sort of the official way, is that on a small scale map, you're zooming out, okay? So the objects will get small, right? New York becomes smaller on the map as you go out, out, out. Whereas on a large scale map, objects get bigger, 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 bigger in your face. You're zooming in. But that's not technically the real definition. The definition is based on the actual number, the representative fraction, being bigger or smaller mathematically. So then we have the directional sign. We said we need something to tell us where at least north is, and we can figure out east, west, and south from there. And that could be a simple north arrow like you see on the left. It could just be literally just a pencil and an arrow with the word N, the letter. It could literally be just a simple arrow penciled in with the letter N below it. Or it could be some combination of the directions. Or it could be a compass rose, which is more complex. It has north, south, east, and west, along with the in-betweens, the cardinal directions, and the ordinal directions. So they have northeast as well, southeast, southwest, northwest, and even in between those. That's called a compass rose. So it looks like a flower blooming. So on most maps, north is up. It's usually, you open a map, usually north is up. But it's not always the case. So you can think for a second, when would that not be the case? When would north not be up? It's an interesting question. You might want to pause the video for a second and think about that before we go to our next slide. So here's an example for you. Which way is north on this map? This is a map of Antarctica, and it's showing the bottom of the world looking down on the South Pole in the center. South Pole is in the center. So which way is north? Think about that for a second. Maybe pause the video, try to figure it out. Maybe you figured it out. So the answer is that on this map, north is every way that's the opposite of south, and south is the dead center of the map. It's the South Pole. So basically, anything that sprays out directly from the South Pole in all directions, so like a star or something in every direction like that, is north. And so what it really is following the lines of longitude, which actually all converge at the South Pole. All these lines longitude come together there, so they're all going to go out like this. It's every line that goes out is all north because they're all going to end up at the North Pole on the other side of the world. Pretty wild, right? So that brings us to the graticule, the grid of latitude and longitude lines. We talked about longitude before, all the longitudes going out from the South Pole. And these lines have names. So all the longitudes are called meridians, and all the latitudes are called parallels and meridians. Remember, parallels we know are all parallel. Not every map shows latitude and longitude. They don't all bother to put the parallels and meridians on there, but many of them do. And so you can say we have a map with a graticule and a map without a graticule. In Geographic Information Systems, there are easy ways where you press a button and the graticule pops onto the screen, and press another button and it takes it off. And it can also just, with another button, change the increments. You can go in 10s or in 30s or anything you want to do. You can make the graticule in the increments that you want it to be. Now let's look at a few extra map elements, which I'll just throw at you here. You have a locator versus an inset map. They're kind of like opposites of each other. So the first is a locator map. A locator map zooms out, so you can see the bigger picture. Where am I? The larger region. So for example, on the left, the big map on the left says Kyushu, big island. But most people don't know where Kyushu is if you're not from that area. So well, where am I? And then you look at the bottom left, there's a locator map there that shows you, oh, Kyushu is at the bottom of Japan, very south end of Japan. Okay, now I know what we're talking about. So it's located Kyushu. It's a locator map. It zooms out. The opposite of that would be to zoom in, which is an inset map. So there's Nagasaki Harbor right there on the right. They've zoomed in to one part of Japan in detail. Okay, so all of Japan, we're zooming in to get one part in detail. That's an inset map. Then the last thing on here, the neatline. The neatline is all those brown boxes around each of the maps there, brown and then black boxes at the bottom. So that's showing you that we're no longer on the map anymore. It's the limits of the mapped area. And it seems sort of obvious, but it's actually important, because if you have a book, for example, you have a page in a book and it's showing you an island, and then it doesn't have a neatline, and the map actually ends here, but the page in the white space goes out to here, you may think that there's just nothing in the ocean out here past, where the map actually ends. Whereas in fact, there may be a continent right there. There may be a bunch of other islands there. They're just not showing because the map is not explaining where the end of the map area is. So the neatline is important to show where the map stops. A map projection is a very important aspect of cartography. And we'll have a whole other set of videos just about that. But a map projection is a method of representing a three-dimensional Earth. Right? The Earth is a three-dimensional globe on a flat two-dimensional plane, whether it's the piece of paper or the screen or whatever. And you get three-dimensional globe to a two-dimensional plane. And the way they do that is basically using math. In other words, you have to be able to have a mathematical method of taking each point on the three-dimensional globe and saying that goes here on the two-dimensional surface. Where does New York go on 2D? Okay, here's 3D New York, where's 2D New York? Here is Richmond in 3D, where does Richmond go on the map in 2D? That's the idea of a map projection. It's a method of doing that. And in terms of 3D geometry, look on the left there. These are some of the basic families of projections, which again, we'll get into in another video. But if you sort of imaginarily take the world and put the map on the top of the world, touching at one point and spray the world onto it like that, you get something that looks like what we saw earlier in Antarctica at the bottom there, a round map. That's called often a planar projection. If you have a conic projection, like a cone, like a party hat in the middle, then that might touch in the middle latitudes like you see there. And that projection produces something like you see at the bottom. Okay, like unwrapping that party hat like that. And if on the right you have a cylindrical projection, like a tube like that goes around the world, that one happens to be touching at the equator. So you unwrap it, and then it looks like what you see at the bottom. The famous Mercator map is like that. It's a cylindrical map. Each one of them has a reason for doing it. There's a reason why you might choose each one of these, and we'll look at those more in another set of slides. But it's just important to know that that is a map projection. And on a map, you often see the map projection written on the map. So you'll have your legend, let's say, and the date and the author, whatever it is, and then it'll say what the map, it'll actually name it. Okay, so if it's a planar projection, or if it's a Robinson projection or Locator projection, it'll actually write that out on the map, and you can read that. One other thing you might find on a map is known as a cartouche. This is more of a decoration used to highlight something, to make something stand out. So on this particular map, that big ornate drawing there on the left side, that's a cartouche. And there's all different kinds of cartouches depending on the culture that it was drawn in, or the map maker themselves and their own taste. So now that we looked at a little bit of the theory of maps and the elements of maps, now let's look at some different types of maps. And there are many different types of maps, which you can see listed here. We're going to go through all of them: reference versus thematic maps, political versus physical maps, Choropleth maps, topographic maps, topologic maps, and then cartograms. And just to be clear, it's not always exclusive. In other words, you can be political and physical. You can be topographic and political. You can be lots of different things. But there's a couple that are exclusive. Okay, generally speaking, a map is reference or thematic, for example. Otherwise, you can kind of mix and match many of these. Let's take a look. Let's start with reference versus thematic maps. A reference map is sort of like a reference book. If you open a reference book, right, like a dictionary or a thesaurus, you're not looking for stories and special angles on things. You're just looking for the basic data, okay? And in geography and cartography, we call it base data, the basic locations of things. Where is Florida? Where is that river? Where is this city? Stuff like that. It's called base data. So reference maps show only the base data and nothing special, no other information. It's not going to say what the tax rate is in that city or that county. It's not going to tell you the number of penguin density, of that region. It's just going to tell you the base data. So this would be your typical, atlas, general atlas, or a wall map or something like that, or a street map, things like that. And in these types of maps, reference maps, which are all around us, the title of the map is often just the name of the place that the map is. So the title of this map is Florida. Here's a reference map of the bottom of the ocean under the Indian Ocean. And sure enough, at the very bottom on the right, you can see the title is Indian Ocean Floor. This is back from 1967, I believe, back when there was, before computers did cartography, they did stuff by hand. It's unbelievable. This is from National Geographic. And National Geographic magazine used to, for many, many years, provide really good maps inside of their magazine that you could pull out, for many months of the year. And it was something that people look forward to get, this month's map from National Geographic. So that's a reference map. By contrast, a thematic map is just like it sounds. It shows some special theme, some special information about the features on the map. Okay, so we saw a map of Florida before. It just showed the base data. And to be clear, thematic maps can also show base data too. You still might see, cities and rivers and stuff like that. But the difference is that on a thematic map, the base data is just there as a background, like the stage that the theme plays out on. Okay, so on a thematic map, the base data is just a background for the theme, the special information. In this case, you see the counties of Florida, but not just the counties. You see a theme about them. How many people under 18 years old by percent? Okay, so take a look at this map. See if you can figure out what county has the most people under 18 years old. I'll pause the video for a second and see if you can see that. Okay, maybe you found it. It's Hendry County, right there at the bottom of Florida. Why is that? Who knows? We could think about that. But Hendry County, because it's got the highest percentage blue on the left. Okay, so a thematic map shows some special information. It could be rainfall, penguin habitats. It could be the income levels, all kinds of things in a thematic map. So let's take a look at some interesting thematic maps, knowing that many times, instead of having a reference map where just the name of the map is the place, Florida, a thematic map will have the name, the title of the map be the theme, whatever that theme is. So here's a map with the theme of French wine regions. And sure enough, the name of the map is France wine regions. That's the theme of the map. And so you can see that somebody really likes wine. This is actually from a website called The Wine Guy. So if you have a website called The Wine Guy, you like wine. And this is showing you the various wine regions of France, how big they are and the extent to which they produce red versus white wine at the bottom. I didn't realize myself until I looked at maps like this that there's an actual place in France called Champagne. If you get champagne in a bottle, they can't, legally make it champagne on the label, write that, unless it's actually from a place called Champagne, the Champagne Valley up there on the top right. Here's another thematic map. This is from one of those famous National Geographic maps that used to be pull out from inside the magazine. This is many, many decades ago. Peoples of the Middle East, right? That's the theme. And of course, you see all over the map, different peoples of the Middle East. So there's another good example of a thematic map. One of the most famous thematic maps of all time is the map that sparked the field of epidemiology, the same field that led to the study of COVID and trying to contain COVID. Epidemiology is a study of epidemics, and specifically spatial epidemiology in this case, and using maps to solve problems about epidemics. A guy named John Snow, you see on the right there, this is in London, studied cholera in 1854 because there was a cholera outbreak. London during the Industrial Revolution was a very grimy place and lots of diseases were spreading. And nobody knew what was causing the spread of cholera. They thought it's in animals, it's in the air, it's just in who knows what it's in. And he made a map that showed where the cholera cases were. Where are people actually getting cholera? And so you see, this is right in downtown London on here. And all those little black marks like this that are stacked up at different locations like that, those are people who got cholera. These are cases of cholera. There are more cases, the bigger the stack, like at each particular location. So he kept recording on the map, doing cartography, until he finally saw a pattern. And if you look closely, take a look and see if you can find the pattern on here. It's right in the middle, right? And here it is on Broad Street. It says there's a pump right here, but look, there's all these people getting cholera right there. They looked high and low for what was the cause, and they went inside this pump. They pulled it out of the ground. They looked inside, and it was all nasty, full of bacteria, gunk, and stuff like that. They realized this is an infected pump. People are getting cholera from this pump, and that's how they realized that cholera is what we call today a waterborne disease, as opposed to a vector-borne disease like through bugs and flies and mosquitoes, things like that. So they used a map to solve an epidemic, solve a cholera problem. So that's the beginning of spatial epidemiology and another example of a thematic map. One of the funkiest types of maps that you'll come across is known as a cartogram. And that's a thematic map that's been distorted so that they take a particular theme, in this case, world tourist destinations, like the amount of people who go to different countries in the world by comparison as tourists. And you then change the area of the country, right? The area of the country, depending on how many tourists they get. So if your area is normally this, but you get a lot of tourists, it's going to be a bigger country. But if it's a small amount of tourists, then your country will shrink. You can see on this map which countries look like they have the most tourists, right? Obviously, in the middle, you have France and Spain and Italy. It's very, very inflated. But take a look at this map, also a cartogram. And in this map, the statistic that's been used to distort the area is amphibian diversity. So this is actually the opposite, right? Because in this one, the northern hemisphere was, generally speaking, was inflated. But here, the southern hemisphere is the one that's largely inflated because they have much more amphibians down there than in the northern hemisphere. So it's interesting to see what you get when you create a cartogram by using some theme, some variable to distort the areas on the map. So now that we looked at reference versus thematic maps, let's take a look at another distinction between maps, which is political versus physical, knowing that many maps can be both of these things. But a political map is a map that shows the boundaries of political units. For example, the boundaries of states, of cities, of counties, of countries, et cetera, things that are man-made, okay? The territorial boundaries that people put down. That's a political map. So that map on the left there, you see it just has states and cities and capitals. That's all it has. There's no mountains on there, no rivers, nothing. On the right, you have a physical map. A physical map shows natural features, which are called landforms. So it also shows states too and cities, but this one is predominantly designed to be physical because you see all these mountains through there, the Blue Ridge Mountains, plateaus, lowlands. So a physical map versus a political map. And the reason they don't always make them combined is because it can get very cluttered. If you start putting everything on the map, all the mountains and all the cities and all the rivers, then it gets to be kind of like spaghetti, like we said, and it's very difficult to read. So by separating out physical versus political maps, it allows you to focus in and with more clarity on those particular features that it shows. So another type of map that you often see, especially in, say, newspapers and things that are trying to convey information, is a Choropleth map. Choropleth map is showing the level of some statistic using shading or colors. So on this map here, you see that the statistic being shown, the statistical variable, is population density. So on the right, it tells you that the darker colors have a higher population density. So you could look in the map and pause the video for a second, try to figure out what's the densest state in the United States based on this map. And you may have seen that the densest state in the United States is New Jersey, right? Because it's the darkest color on the map, which is amazing because Rhode Island is a very small state, and yet New Jersey is still more dense. So that's an example of a Choropleth map using shading to show a statistic. And in Geographic Information Systems, you can press buttons and determine where the boundaries are. So for example, on the population density on the right, it says 0 to 20. Well, you can make it 0 to 30 or 0 to 40. You can make each category different depending on whatever you want to do, whatever you think is most meaningful, easily using Geographic Information Systems. And here's the other option. We said that you can use shading or colors. This one's using colors. So it goes from purple to blue to green to yellow, right? To show how many religious adherents, how much people that are religious in each county across the United States. So the higher the religiosity of the people in the county, the more yellow it is. And the less religious, the more purple it is, more blue and purple it is. So it's very interesting. You can see on there, which parts of the United States are more religious and which are not. A very common and very, very useful type of map is a topographic map. A topographic map is any map that shows ups and downs, shows the elevation across a region, the variations in elevation. This is Ethiopia, and you can see the Ethiopian highlands there have a lot of variation. And that's known also as relief. A relief map is an elevation map. It shows how much the landscape is extruded up above sea level like that. So there are many ways of showing elevation on a map. You could use shading, like you see on the right there. It's got some darker and lighter. You could also use Choropleth as well, which you see on the right there. In this case, colors to show different elevations. But one of the most common ways of showing elevation on a topographic map is contour lines, lines like this. These are lines which all around a single line, as long as you're following one line and staying on that line, it's the same elevation. We'll have a whole a whole lesson just on this, but I just wanted to show you what a topographic map is and what these contour lines are. And to contrast with topographic maps, like we just saw, there's another word which is completely different meaning, but sounds a little the same. And this is much less talked about, but I threw it in here just because it's interesting. It's called a topological map, not a topographic map, but a topological map. Remember, topos means place. So, for example, if I have the study of place names, like city names and state names and country names, it's called toponymy. Toponymy, the study of place names. And the name of a place is called a toponym. So Richmond, Virginia is a toponym. It's a place name. So a topological map is showing a simplified version of the world so that only some vital information is on that map. Okay, so you look at this napkin, someone was in a bar or something, eating a hamburger, trying to explain something to somebody. And they just wanted to capture the essence of their point. They didn't want to draw every single feature, didn't have time, probably couldn't do that. So they just wanted to capture what in Greek they called the logos, right? The idea, the thought, the essence of something. The scale was not important, but they wanted to get the idea across. Pause the video for a second, see if you can figure out what is the idea that this person, imagine he's, scribbling on the back of this napkin. He or she was trying to explain. What were they trying to explain when they drew this map? So on this map in the middle, you can see it says 5 days straight. 5 days straight. It looks like, okay, there's Minnesota down there, there's Toronto, Vancouver. So basically, that's Canada up there. They're driving from one end of Canada to the other, basically, from up in British Columbia above Vancouver, all across Canada to Montreal. And the funny part is, one of the funny things of this map, he's got the line going straight through what appears to be a bay up there. But that's okay, because it doesn't matter, because this is just a topological map, right? It's not supposed to be perfect. It's just trying to capture the idea. And does it work? It does, right? He's saying you can drive from one end of Canada to the other in 5 straight days. It doesn't matter whether it's perfectly drawn or not. Here's a topological map that I'm very familiar with because I grew up in Northern Virginia, and I took the metro into DC to go to high school every day for several years. So I grew up way out here at the end of the Orange Line at Fairfax, Vienna, George Mason University stop out there. And I took the metro all the way into over the river to Gallery Place. I'd switch to the Red Line and then go up into Union Station or Brookline later. I switched schools and then get off and walk to school. Notice that every single stop on the orange line out here is exactly the same distance apart. Every single stop on the red line here is exactly the same distance. Do you think that's really how it is in real life? In fact, these stops are actually much farther apart out here at the end of the orange line than the ones downtown. So why would they draw the ones downtown further apart? Because there's no other clutter out here. You just have one line. You don't have to worry about, okay, where am I? It's not going to get just, lost amongst many stops. But downtown, there are many lines coming together. It gets very hairy in there, very complex. So they blow it up in order to show each stop clearly and the relationships between them. Because if you put them close together like this, it would all become spaghetti really fast and extremely confusing. So they did the opposite of true scale. They made things that were closer together further apart in the downtown area to show them with more clarity and detail, while putting things that are farther apart closer together out here, because the detail didn't matter because there's only one line. You can't mistake it for another line or get confused with other stops because there is just one line. Just for comparison, here is the real world scale of the metro. Look how far, when you go out here, these stops go way out. They're so far apart, but here they all look like they're just bunched up together or tightly. Okay, so it's real world scale versus topologic scale is not true, and yet the topological map works. So those are some different types of maps. Now let's look at a field that has been growing exponentially in the last several decades called Geographic Information Systems. And it's known as GIS. GIS is a field that is not just this or that. It's not just one thing. And let's just quickly clarify that it's not the same as GPS. GPS is the device on your phone, or in your car or in any device that tells you your location on Earth using satellites. GPS stands for Global Positioning System. So GPS is a subfield within GIS. GIS, Geographic Information Systems, is much wider than just GPS, but you can use GPS within GIS. So Geographic Information Systems is basically using all of the tools of IT, computers, databases, programming, languages, all that different stuff, along with all kinds of geographic data that you might collect out in the field, sometimes using GPS or using satellites or using airplanes with cameras or whatever it might be, using just knowledge that you have in your head. And you go out, you put all that data into computers, into information systems, and you get the data supporting maps. In other words, you have maps that are sort of filled with data. Okay, so at the bottom, you see there's a physical map right there. But what it's trying to show is that underneath that physical map, so to speak, in the computer, there's all this data. Like it says parcel owners, parcels of land behind it, who owns it, and how big is it, how much does it cost, stuff like that. And there's all these different things that you can have underneath of it, where fire stations and Starbucks locations and tax rates per county or whatever it is that's in the databases that fill up that map. Okay, so Geographic Information Systems can take information from anywhere and then put it into maps. One of the core features of Geographic Information Systems is using map layers. And you could put, for example, a simple example on the screen, and you can take your street data, right, your reference data about streets, then add your building data layer on top of that, your vegetation layer on top of that, and then you can see, okay, which streets have a lot of buildings and a lot of vegetation and which have less, and what's the relationship spatially between them and all that. But you could put anything on there. You could have 100 different layers of information, and you can then run complex functions. You can ask questions about the data layers across the many layers by having these queries that you write out to see, okay, which of these streets has the highest disposable income in a particular area and the easiest to get to a particular shopping center. And, maybe that's where we want to put our new Starbucks, something like that, where people have money to spend on coffee. So you can put and they do that. They use that GIS to determine where to put new stores, where to put stadiums, where to put firehouses, where to put new schools, so that the most amount of people who would need to access that can access that. It's called location science. It's very interesting. Here's a different type of GIS example. not of Starbucks, but of rock formations. So you can see that on the left here, this is a software called ArcMap. It's made by Esri, which is like the Microsoft of GIS, so to speak, the big company that makes most of the software. You have your many layers of data on the left. So you've got, they have open a rivers layer, a faults layer, a folds layer, a sheeting layer for the elevation, and then a formations layer, which has all the different like periods in geologic time to tell you when that formation was created. Okay, so down here, early Proterozoic, et cetera, to get through all Holocene, right? The gray, which is the Ice Age, basically, and Jurassic, the time of dinosaurs down here. So you can look at the different rocks on the screen and say, okay, it tells you by shading what period in geologic time that was created. And then you can see where the folds, the faults, the rivers, and all this are. All those are different data layers that somebody collected and created, but you put them all together and you can ask questions across them. You can ask queries to figure out how does this layer of data relate to that layer of data to answer important questions. Geographic Information Systems is used by all kinds of businesses and individuals too, across the world, not just in the United States. But it's especially used by governments and also by schools like universities doing research, things like that. And if you're interested in a career and kind of like this stuff, you like maps, you like computers, you like IT, then there's for sure a lot of jobs in GIS, in the military, in federal government, in state government, and also in local government, right down to the town level. There's actually a lot of jobs in local towns, planning, things like that, that are going to use GIS, and they take, okay, here's the water pipe system, and here's the road system layer, and here's the schools layer, and how can we make it all work together? So there's a lot of GIS jobs at the state, local, county, city, town level. As I said earlier, the biggest company that by far that makes GIS software is called Esri. You see the logo on the right. They have a website, actually has lots of tutorials, lots of information if you're interested about that. And the US military on the bottom is one of the biggest GIS users in the world. And finally, along with geographic information systems, there's another field which goes together with it called remote sensing, which is literally exactly like it sounds. It's getting information, sensing from a remote location, from far away. So anytime you're acquiring information using a sensor from far away, you're doing remote sensing. People usually think immediately of satellites, which is one of the typical types of remote sensing. There are many, many satellites types that go around the world monitoring all kinds of things, from weather and clouds and winds and things like that to the temperatures of the oceans. But there's also remote sensing of other types as well. For example, there's this ocean sentinel nomad, which is a floating buoy in the ocean. There's nobody on there. They just put it out there and it senses the weather conditions, the ocean temperatures and current directions and salinity, the water quality, all kinds of these. And then you can put these all over the world, those buoys like that, and then they can report back using signals. They send the signal back to the satellite and then it bounces to the laboratory. They can easily monitor weather and ocean data all around the world. So you can put thermometers, lasers, barometers to measure air pressure, microphones, all kinds of things that could be your sensor out there that's reporting back to you from far away. For example, you could put a camera inside of a tree, make a little hole in a tree somewhere in Siberia in Russia. You dig out a hole, you stick a camera in there, and you have that camera run all year long, hoping that you're going to find an Amur leopard, a Siberian leopard, pass by. You're like, I wonder if the Amur leopard is in this habitat. And you run that camera that's hiding inside of that tree for a year. And after a year, you go get it back, you bring it to the lab and you play it fast forward. There it is. There's the Amur leopard right there. So you can catch animals sort of on video through remote sensing like that. I have a friend who's actually from Virginia and a former student in one of my classes, and he posts pictures online of his infrared night vision cameras that he has in the back of his house at night. And so you can see foxes and deer and possums come through at night and try to find food and things like that. It's very interesting. And that's remote sensing. So here are some examples of remote sensing technologies. As we said, the usual one people think of is satellites, and there are lots of satellites. But at the same time, there's also just planes. You can have aerial photography is a very common thing, especially in the military. That's, for example, how we discovered that Russia had missiles in Cuba during the Cuban Missile Crisis was through remote sensing. America flew planes over Cuba, and we took photographs, and we could pinpoint that there was something going on. These missiles were sitting there in Cuba. And you have balloons, weather balloons that can go up there. You can have aerial drones, UAVs, unmanned aerial vehicles down there. All these different types of ways that you can get a sensor out there, these vehicles for sensors. And the things that they monitor are many. They could monitor the loss or the gain of ice, sea ice over on the right, up on mountains or in the ocean. You can monitor the amount of aerosols, which are particulates, like fine solids up in the sky that are floating around up there, suspended in the air. You can monitor the temperatures of the oceans or the currents, all kinds of things that you can monitor using satellites alone. So there are many types of satellites monitoring many different aspects of the world. And satellite images collected through remote sensing are often used to monitor some type of change over time. They're very good for monitoring large-scale change because they have such a zoomed-out view. So, for example, here you see in Pakistan, there were major floods in 2022 in the summer, and on the left you see before, and then on the right you see after. That's an area that's usually is a desert or semi-desert region, so there's not much vegetation there on the left, on the edges there, and suddenly it's full of blue all across it, right? Many people lost their homes, had to migrate. It was a major incident, these 2022 floods in Pakistan. So these two pictures, sort of the before and the after, capture it really well. And there are many, if you're interested in this kind of thing, if you Google remote sensing or satellite images before after, you can see all kinds of what happened before and after a hurricane, or even the creation of the islands, artificial islands, like in Dubai and things like that, where they had nothing and then they build the Palm Islands out of nowhere. So very interesting to see before and after images taken by satellites to monitor change through remote sensing. And you may be wondering, well, remote sensing, is that cartography? Because is it technically a map? It's more like a picture. And you're absolutely right. It is a picture. It's not a map. But what they do with remote sensing is they take a remote sensing image, and then they will, what they call drape it or impose it onto a surface. And you can actually match up certain points. So Islamabad is here on the map, and then you find Islamabad on the image, and you attach it like that. Okay, so you can anchor certain points of the image to points on the map, and then put it on there so it becomes literally both a map and a picture at the same time. You can superimpose the images onto the map and then anchor them so it's matching up correctly to the map, so that you have map locations showing dots and lines and things like that, but then the images all around it giving the landscape view as well. So that's a look at cartography. As we said, maps are the primary tool of geographers. They allow us to know where things are, which allows us to then look at that and then think not only where they are, but why, and so what, and figure out what really matters. And that's how we spot patterns when we're doing geography.